were cases of facilitated diffusion. They were moving things with a concentration gradient. If the channel's open, things will move with the gradient. You can open and close the channels that way. If the carrier, under certain conditions, is going to bind something on one side and move it into the side, but again, with a concentration gradient. If we move things against the concentration gradient, that is called active transport. So active transport goes against a gradient. Now because of that, what that means is you're transporting something from a low concentration to a high concentration, right? That means you're transporting something from a low energy state to a higher energy state, right? Endergonic or exergonic? Endergonic, right? So to drive this, we have to have an input of cellular energy. Now the most usable form of cellular energy would be ATP. Right? So ATP can break down into ADP plus PI, and that releases energy, and we could use that to do the transport. Right? If we use ATP as an energy source, it's called primary active transport, and these things are called pumps. So a proton pump. There are proton pumps in the epithelium of the stomach. They pump hydrogen ions out into the lumen of the stomach to increase the acidity, right? To help in digestion. Does it take energy to do that? Yeah, because they're going from a low concentration to a high concentration. You're pumping them out. Right? There are sodium pumps that pump sodium, potassium pumps that pump potassium. And I think I mentioned one pump in particular where a third of all of your ATP goes. ICF, there's your ECF, and there is this pump called the sodium potassium pump. It uses ATP, hence the name of pump, so it's primary active transport. Every time it pumps out free sodium and pumps in to potassium. So it's carrying both of them at the same time in opposite directions. That doesn't really matter. But a third of your total energy budget is going just to keeping sodium out of the cell and potassium in the cell. We'll see why as we work our way through this, that there's always sodium coming in and potassium going out, so we always got to keep pumping them back the other way. So these pumps do that. Now, that is called primary active transport. You can do secondary active transport. And secondary active transport is where you use this is just all sodium potassium pumps there, is where you use the energy from some other source other than ATP to drive the transport of something else. And more often than not, what we're using is the diffusion of sodium. So we let sodium diffuse in, and we use that as an energy source to drive the movement of something else. For example, let's look at this case right here. This is an SGLT, we say S-GLUT transporter, stands for sodium glucose transporter. It is an example of secondary active transport. And what we're using is the energy from the diffusion of sodium to drive the active transport of glucose. For example, here, sodium's in a high concentration outside of the cell and a low concentration inside of the cell. So in which direction will sodium diffuse? Into the cell. Exergonic or endergonic? Exergonic, right? From a high concentration, high energy, to a low concentration, low energy. And as that energy is being released, we're going to use that to actively transport glucose here from the low concentration inside of the cell. Oh, I'm sorry. Actively transport glucose here from the low concentration outside the cell to the high concentration inside the cell. So glucose comes in, right? Low to high, that's active transport, that's endergonic. This protein carrier couples that reaction. It couples the exergonic diffusion of sodium with the endergonic active transport of glucose. So this would actually be called a sodium glucose co-transporter. They go in the same direction, so it's co-transporter. Sometimes that's also called SIM, which means together, SIM porter. So a sodium glucose SIM porter, they go in the same direction.